Static force analysis. This is a machinery problem. We've got a 4-bar linkage with multiple forces on it, and we're trying to find the torque that would be required to hold the system in equilibrium. But static force, think statics. This is just a big statics problem. And so your machinery course might seem pretty tough to find all the velocities and inverse kinematics, but static force analysis, again, think back to sophomore year. Statics was really hard at the time, but hopefully looking back on it now, it seems really easy to you. And so this problem is going to be tough from a geometry, trigonometry point of view to find all the distances we need. But fundamentally speaking, free body diagrams and sum of forces in the X and Y direction and sum of moments, that's really the whole thing. So I'll get started by drawing a free body diagram for link 2, the crank. So I'm going to have a pin joint at O2. So I've got forces F2x and F2y, a pin joint at A, FAX and FAY, and 30-degree angles and two distances here, AX and AY, and of course the applied torque. That's going to be the final answer that we're looking for. Unfortunately, as I add all these up, there are 5 unknowns, and thinking back to your statics class, for a 2-dimensional problem, you only have 3 equations, sum of forces in X, sum of forces in Y, and a sum of moments. You can only solve for 3 unknowns. So as I plan ahead a little bit, I think to myself that if I can find FAX and FAY somehow separately, then I could do a sum of moments about 0.02, and that would let me solve for torque. So that's my goal. So I need another free body diagram. I'm going to have to do other work, but eventually when I come back to this, I'm never going to care what F2x and F2y are. So if I find FAX and FAY, sum of moments, that'll get me to the answer. And in fact, I can even write out that equation right here. So the sum of moments about 0.2 is 0. I will call counterclockwise direction positive. So my equation will be T2 plus FAY times AX plus FAX times AY. So it turns out I don't only need the 2 forces, I also need those distances, AX and AY. Fortunately, those are not super tough to know because I know the length of this arm is 75 millimeters, and I know the 30-degree angle is also given. So I can solve for AX and AY right away. Just 0.075 cosine 30 and sine 30. Get 0.06495 and 0.0375 is those 2 distances. So now I'm back to where I thought I was a minute ago of only needing to solve for those 2 other forces, FAX and FAY. And that's going to mean another free body diagram. You didn't really think there was only going to be one. So drawing the free body diagram for link 3, this is the big triangle link here in the middle. I've got points A, B, and C. At point A, I've got the same 2 forces from my first free body diagram, right? It's the same pin is attached to point A to both links, so FAX and FAY. But my vectors on this diagram are pointing in the opposite direction. Internal forces need to cancel out. So if you have the same forces on 2 different free body diagrams, they need to point in different directions on each diagram to, again, cancel each other out. I've got the force at B that's pointing upwards at a 45-degree angle. I've got a force at C that 1800 horizontally. And for link 4 is a 2-force member. It's only attached at the pin at C and the pin at O4. This allows me to just place a single force there. I do not need to put an FCX and an FCY for that pin joint. Normally a pin joint would require 2 forces, but for a 2-force member, we do know the direction. The direction has to be in this theta 4 direction, the direction that link 4 is pointing, because it's a 2-force member. If there were any forces acting in the middle of link 4, that would not be true, and we would have to include 2 forces here. We would have to include a CX and a CY. But for this case, I'm just going to label theta 4 along with FC. So now I'm starting to think ahead. All right, I'm going to start doing a sum of forces in X, sum of forces in Y, sum of moments. If I'm going to be doing a sum of moments on this free body diagram, I also need lengths. So bx and by, cx and cy are going to be the 4 relevant horizontal and vertical lengths for this free body diagram. And the good news is there are only 3 unknown forces on this drawing. There's still the 4 lengths that I don't know, and you can probably guess that's actually going to be the really hard part of this drawing, is finding all these lengths. That's going to be what takes the most time. But if I just write them as constants for now, I'd actually start writing out the problem. So a sum of moments about point A is going to allow me to solve for FC as the only unknown. And then later on, I'll be able to do a sum of forces in X to find FAX and a sum of forces in Y to get FAY. So sum of moments about point A, if I look at first the 500 newtons, I'll take the vertical component, 500 sine 45, and multiply that by the X distance. A moment needs to be a force and a distance that are perpendicular from each other. So a vertical force times a horizontal distance. And then when I do the horizontal force, 500 cosine 45, I multiply that by the vertical distance, by. If I'm calling counterclockwise as positive, then the 1800 times cy will be negative. The FC, the vertical component, will be in the positive direction, so plus FC sine theta 4, and then times cx. And then the horizontal component of FC is going to be times cosine theta 4, and that will be times cy, the horizontal force times the vertical distance. And now I'm letting you know in advance that I plan on cheating a little bit here. So I put plus FC cosine theta 4 times cy, but theta 4 looks clearly more than 90 degrees. So cosine of theta 4 is going to be a negative number, but I'm making a mental note for myself that I'm only going to take the magnitude of this value because I know that that whole term has to be positive. I'm calling the counterclockwise direction positive, and the force is pushing to the left from above point A, so it's going to be counterclockwise. So that expression is going to be positive. So even though this cosine term is going to give me a negative answer, I'm going to ignore the negative sign and just keep this part of the expression positive. That's kind of cheating. And if you don't think you could remember that for yourself, you might want to actually do that as a negative term, or instead of using theta 4, you might want to use 180 minus theta 4. So you get the angle underneath the red arrow there instead of the big open arrow from the positive x-axis. So let me add a couple of numbers to the drawing here. The 150, 200, 300, these are my lengths for the triangle, because before I can finish and evaluate this expression to solve for FC, I'm going to have to find bx, cx, by, and cy. And this is probably going to be the most annoying part of the problem. Oh, and theta 4, we need that one also. But yeah, doing the actual geometry, trigonometry of this, that's the hard part. The statics of it, the sum of forces and sum of moments, the statics part's the easy part. It's actually just trying to figure out all of these distances to do the moments. That's actually going to be kind of the hard part and the frustrating part of this problem. Let's find theta 4 first. On my original drawing, I'm going to draw a diagonal line from A to O4, from the end of the crank to the ground that the rocker is attached to. This diagonal line is going to split my 4-bar linkage into 2 triangles. But this is the normal first step for analyzing a 4-bar linkage, that if you've solved for transmission angle before, this is that same diagonal line that you always start with. So this is going to give me 2 triangles, an orange one and a green one. And from these 2 triangles, I can find theta 4 as 180 degrees plus phi 1 minus phi 2. And that will give me theta 4. Normally in the open configuration, 180 would be the sum of all 3 of these. Theta 4 plus phi 1 plus phi 2 would all add to 180 degrees. But since the green triangle is dipped below sort of the horizontal line, so theta 4 plus phi 2 actually go past 180 degrees, and you have to come back by phi1 to get back to 180. So this has been a very long way of me saying that I'm gonna draw these two triangles down here further below, orange and green, and solve for these two angles, phi1 and phi2, and I'll use them to get theta 4. So first I have to solve for this distance L, and I'm gonna use the orange triangle for this one because on the orange triangle, I have this 30-degree angle already. So I have two sides and an angle, which means I can solve for L using law of cosines. I'm gonna be using a lot of law of cosines. So L squared, and then the 75 and 400 are the two adjacent sides with 30-degree angle. I get L of 337.1. And to find phi1, I can do another law of cosines. So now from phi1's point of view, 75 is the opposite side. So that's the expression on its own side. L squared and 400 squared, along with cosine of phi1. Phi1 ends up being 6.38 degrees. Kind of makes sense. You can tell that this is a really skinny, small angle. It's a skinny, small triangle. So now I draw the green triangle, sides 300, 200, and this 337.1, and I can solve for phi2, also by law of cosines, with 300 being the opposite side from that angle phi2. 61.84 is phi2, which now lets me solve for theta 4. 180 plus phi1 minus phi2 is equal to, gives me theta 4 of 124.54 degrees. And you might be thinking to yourself right about now that, oh good, we drew a couple of triangles, did a few law of cosines, we're probably done with that now and we can go back to the free body diagrams. But no, of course not, right? This only solved for theta 4. There's still 4 other distances we need to find. Bx, by, cx, cy. We still need to find all 4 of those. There's definitely going to be more triangles still to come. But trigonometry is not the only tool that we have available to help us find distances. I think for finding some of these x and y distances, it might be easier to just think of ourselves as, to think of this triangle as existing on a coordinate axis. And so if we put the origin at O2, then we can find the coordinate, like the xy position of point A, as being these x and y coordinates that we found, the 0.06 and the 0.0375, right? That's the xy coordinate of point A. And now that we've found theta 4, we can give a coordinate for where point C is located in space. In the x direction, it's 400 in the x direction for ground, plus 200 cosine 124 in the x direction, and the y direction coordinate is just 200 sine 124. So instead of going like from A to B and B up to C to find where C is located, we can actually go from O2 to O4 and from O4 up to C. And that gets us an xy coordinate of point C of like 0.28 and 0.16. So if we subtract the two x coordinates and subtract the two y coordinates, we get these values, cx and cy. So cx ends up being 0.2216 and cy 0.2022. And of course, for cy, I left off a negative sign here. The y value at point A is negative 0.0375. So it's not 0.16 minus 0.03, it's 0.16 minus negative 0.03. That's why it got a little bit higher, because point A is below the x-axis. The angle of the crank is pointing downwards. And so now, are we going to be able to do this same technique for point B? And the answer is no, because we don't have, what was nice for point C is we had theta 4 that pointed up to point C. We don't have anything pointing at B right now. So we're just gonna need to start solving for things and then maybe come up with a plan. But so right here on this triangle, I'm gonna go ahead and solve for theta AC as an inverse tangent of y over x, 42.38 degrees, because I think it's going to be useful in finding point B on the next step. In order to find point B, we're gonna look for basically some more angles. It's gonna be more trigonometry. So when I draw this coupler link, this ABC, what I really want is theta AB. I want the angle from line AB down to the x-axis, because then I can do this same sort of coordinates, just length cosine theta, length sine theta to find these distances. But I can only find that angle indirectly. So I just found theta AC, which goes past AB all the way up to the AC line. Now if I additionally solve for angle CAB, this interior angle inside the triangle, then I can get the angle from AB to the x-axis as theta AC minus this theta CAB. So the angle all the way up to AC minus the angle inside the triangle will just give me that smaller angle down at the bottom. So a law of cosines will give me theta CAB. I just using the three lengths of this triangle, the 150, 200, and 300. I get an angle CAB of 26.38, and I subtract that value from the 42.38 that we just found all the way up to C, and that gives me an angle from the x-axis up to B of 16.0 degrees. And that lets me find my bx and by as just 200 cosine 16 and 200 sine 16 as just the x and y components of this 200 length from A to B. And then the 16-degree angle is the angle from AB down to the x-axis. And now, this has been why this problem is so much harder than the problems were back in statics. When you took statics, almost all of your lengths were always given to you. You were never expected to do any of this really, I don't know if this is advanced, but tedious or frustrating sort of geometry, trigonometry to try to find distances and angles. So the sum of forces and moments really is the easy part to these problems. The statics is the easy part. It's actually like the high school geometry of this. It's actually the really annoying part. But now that we got the four distances, we can go back to the statics part. So now we can actually plug in our bx, our by, our cx, our cy, our theta 4. We can plug everything into this big moment problem, finally solve for FC. And again, remember I cheated with the cosine 124. Even though that's going to give me a negative value, I'm still calling it positive because again, I know it's because the moment is in the positive direction. And this gives me an FC value of 930.7 newtons. I can do a sum of forces in the x direction equals 0. FAX is pointing to the left, so it's negative. 500 cosine 45 degrees, also pointing left, so it's negative. The 1800 is right positive. And the 930 cosine 124. But this time I learned my lesson and I am not cheating. So even though I know that FC is pointed to the left, I'm calling the 930.7 positive because the cosine 124 is measured to the positive x-axis. This is the way you're supposed to do it, right? If your angle is measured to the positive x-axis, just call it positive, and then the cosine of 124 will give me the negative sign, right? This is the right way to actually do it. And I get an FAX of 918.8 newtons. Sum of forces in the y direction equals 0. This is a typo. FAY should be negative, right? It's pointed downwards on my free body diagram. I did it correct in my calculator. What I did is I just added FAY to the other side of the problem, right? It's negative FAY plus 500. So then I move the FAY over to the 0 side and it becomes positive. So plus 500 sine 45 plus 930.7 sine 124.4 gives FAY positive 1120.2 newtons. And now we can go back to free body diagram for link 2, the first free body diagram from all the way back to the problem. You can hear my voice getting excited. I'm like, oh, we're just about done. Yes. So we've got torque 2 plus FAY, the 1120, times AX, the 0.064, and then plus FAX, the 918, times AY, the 0.0375, and that gives us torque 2, 107 Newton meters. The nice thing about Newton's laws and free body diagrams is they are familiar to you. You've been doing them for years, ever since statics. But actually for machinery problems, virtual work is usually the better method. With the method of virtual work, along the process of solving for forces, you will automatically solve for velocities, which is super useful. Almost always, if you're analyzing a machine, you don't only want to know forces and torques, you are also interested in positions and velocities along the way. So watch this video about virtual work for another static force analysis example problem solved with a completely different method.